Okay, well, we're getting into stuff that I hadn't anticipated getting into today, but it just all rolls out logically from where we started. And we started from something you were doing at the beginning of class. Okay? So, So, that is your directional derivative, okay? Make sense? Okay. Now, hadn't anticipated I would do this today, but what the heck? Okay? The gradient. Upside down delta with an arrow over it. This is what we're going to call an operator. And this operator is easy enough to understand as soon as I tell you how it operates. Okay? This is an operator. Okay? And it acts like this. Okay? And what that means is, it's kind of like the operation distributes, or, these things distribute over f, so you get partial f with respect to x times I plus the partial f with respect to x times j. Okay? But why didn't I just write this out? Because you can also do a cross product of the operator with a vector function.
Why, on that first one with the operator, aren't you taking the derivative of a unit vector?
No, it's an operator. And the operator is defined by the way it acts, which is this way.
Okay.
That's the only definition. And obviously, what you just said would make sense. If I hadn't already said, we haven't yet defined how this operator works, right? And that's not how it works, because I said so. Not because that is the definition, okay? Does that make it halfway make sense?
Yeah.
I mean, people have no trouble getting used to using this operator, okay? And I remember when I first saw operator, I said, that's weird, okay? But it's easy to understand, so I didn't worry about it. Then I saw, as things evolved and we started doing, divergences and curls with the operator and stuff like that, it's arguably the most important operator in the world. Okay?
There are others?
Huh?
So there are others?
Oh, sure, you can define all kinds of operators. You could define an operator that says, take the y derivative, add an aardvark, and then do the x derivative of that. We can define any operator we want and make up a notation for it, okay? So there's certainly other operators, like the del squared operator. That's just the del operator dotted with the del operator. Okay? Of course, that's based on the operator, and we're actually going to see that relatively soon. Okay? But we don't need it right now, so let's just stick with one application of the operator. Okay? So, there it is. Now, If you use a unit vector in the direction theta, then what are the components of u? Well, u is cosine theta I plus sine theta j. Something which, if you haven't previously grasped, you need to ponder. But it's pretty obvious, okay? I mean, in direction theta, the ratio of the y to the x component is tangent theta, right? Or the ratio of the y component to the distance along the vector, okay, or the length of the vector, is just sine theta, and this one is cosine theta, right? So the vector is some multiple of cosine theta times I plus a sine theta times j. Well, it follows immediately, if you make a unit vector out of that, this is what you're going to end up with. Okay? And again, that's not clear to you, you probably ought to think it through. Okay. Your book also tells you, I mean, in different words, and maybe in a less intuitive way or maybe a more intuitive way than I'm explaining, okay? So I'm not going to dwell on it. It's in your book, and it's easy to understand, okay? And the next thing is easy to understand. Tell me, what do you think del dot u would be? Write it out.